Okay, so let's take a look at this example here where we're trying to compute the area that's inside these two circles. In other words, where the two circles overlap. So we're looking specifically at this area right here, this little slice here, this little sliver of the graph. That's what we want to compute the area of. However, if we look at how this graph comes about, so if we pop over onto Desmos and I have my two graphs in there, and I start looking at the two graphs, I see they do cross the one time there. Okay, coming around, coming around. Now, at this point, when I reach pi over 2, the black graph has come back and intersected at 0, but it's not actually crossing at that point as far as theta is concerned. Physically, it's crossing, but in terms of theta, they're not crossing, because at theta equals pi over 2, the black graph is hitting 0, but the blue graph hits 0 at theta equals 0. So if you're thinking of just going, from here, integrate from here until I reach pi over 2, that's just not going to work. Right? That's actually not going to work. Right? That won't handle it for us. So we have to look at what we can compute. Of course, we can keep going. Right? And finally, when we reach pi, both graphs are complete. So this is the region we're looking for, but we can't actually compute it directly because what we need a point, a line that's coming out and hitting both these points, and that's just not happening here. That's just not happening here. Okay, so, and that's because we can actually do this region okay, because we can draw a radial line from the origin out to any point that falls in this thing. We can see it's this black circular graph. Take away this inner blue circular graph. Right? We can actually compute that. But when it comes to this part of the graph, even though they physically are overlapping, they're overlapping on different angles. And so that makes try to do the integration process just not practical. We would need this to actually be graphing across 0, and it's not doing that. So what we're going to have to actually do here is look at this graph in terms of two things. First, we can compute the area of this semicircle just using basic math. We can compute the area of that semicircle without doing calculus. Now we can do calculus to do it, right? We can use calculus to compute the area of that semicircle too. Right? Let me just turn off the blue graph for a moment and realize that would just be the integral of that thing from 0 to pi over 2. And we could use calculus to do that, but it's actually a lot simpler if we just compute that area using just regular basic algebra. Okay. Then what we can do is we can compute this area, this little section here, by using calculus. Right? And then once we have those two areas, we can just subtract them. So this is not as smooth going as we would like, as some of our other problems were. So what we'll do is, again, compute the area of this semicircle. That's easy enough to do. And then compute the area of this inside little piece here as well. And then once we have that area, we can take the red area away from the blue area to get the area of the little football that we're looking for here. Okay, so that's going to be our strategy. That's going to be our strategy. So first, let's just get the blue area, the area of the semicircle. We can easily see that this circle has a diameter of 3, so it's got a radius of 1.5 or 3/2. So the area of the circle, I'll just call it here, area of the circle, it's just using the area of a circle formula, right? pi times r squared. But it's just a semicircle, so it's going to be half of that. So 1/2 pi times the radius squared. And this would just give us 9/8 pi. Okay? Now we approach the question of how do we do this area of this purple region, if you will, this overlap between the red and the blue, this little piece here. Right? In other words, we're looking at the area that's contained inside this region. Right? That's the thing we want to now compute. Okay? And we can do that with calculus because both of those graphs that make up that region are existing and forming that region over the same interval of theta. So we're able to use those. So that's what we're going to set about now. So to do that, we need to know where this point is. Well, you can kind of increment a little bit on your Desmos to kind of approximate where it's at, or even get it exactly. Or we can just say that's the first place where these two things cross. So that's the first place where these two things cross. So we can just set 3 sine theta equal to 3 cosine theta, and divide both sides by 3 cosine theta, and we get tangent theta equals 1, and tangent theta leads to two solutions of pi over 4 and 5 pi over 4. So the pi over 4 is when they're going to first physically cross, and of course once we get up to pi, the two graphs are done, and what happens is 5 pi over 4 here in the third quadrant, that's when both sine and cosine are negative. That image is actually going to reflect back through, and we're back to the same graphs again once we pass pi. Okay? So the one that we're looking for is pi over 4. All right, this happens at pi over 4. Okay? So let me draw my little line of direction here. Right, pi over 4, that's where it's going to stop. Right, that's where we're going to be stopping. And again, what we are finding is the difference between the area. So the difference between the area of the outer circle here, right, which is just the circle, minus this inner piece here. Minus this inner piece here. And so what I want you to notice here is when you're doing this area to any point on the circle here, it's always going to be the value. It's always going to be the value of the outer graph, and then take away the value of the inner graph on that angle, okay, all the way out until we get to our last point there. Okay, at pi over 4. Okay, so that's how we're going to actually compute that area. That's how we're actually going to compute the area there. So what we have to recognize is that we're passing through the blue graph first, right? And then we're passing through the red graph. So basically, or the black graph, which is now red because I colored it. So what we're going to have to do here is look at the integral for the area of the one region and then take off the area of the other region. Okay, so let's go ahead and do that. Let's go ahead and do that. So that would be, give a name to this area. Let's call it the area of the blobby piece here, right? And that would just be the integral 0 to pi over 4 of 1/2. So for the inner of the first one, that would just be the function squared. So the outer function, let me get the right one here now. Cosine was the black graph, so that's the outer one. Sine was the blue graph, so that's the inner one. Okay. Okay, so we would have 3 cosine theta squared minus 3 sine theta squared d theta. And then we simplify. 3 squareds will be 9. We pull all those 9s out along with the 1/2 and have a 9/2 out front. Integral 0 to pi over 4 of cosine squared theta minus sine squared theta. Now we could pull in those two identities for cosine squared and sine squared, or makes life a little easier, we can leverage the fact that cosine squared minus sine squared is just an identity for cosine of 2 theta d theta. And then we can carry that through. All right, we would need a 2 to go with the d theta, so I'm going to put that out front. And that's just going to make that 9/4. And then we do integral of cosine. Integral of cosine would be sine. So we have sine 2 theta. And then that's going to be evaluated between 0 and pi over 4. And compute that. We plug pi over 4 in. 2 times pi over 4 will be pi over 2. Sine of pi over 2 is 1, so that's just going to be 9/4 times 1. And 2 times 0 is 0, sine of 0 is 0. So that little sliver is going to have an area of 9/4. That little sliver is going to have an area of 9/4. Okay. So that little sliver will have an area of 9/4, this blue area, or the purple area. And we already know the area of the circle is 9/8 pi. So therefore the area of this thing, the region we're looking for, would just be the area of the circle, 9/8 pi, minus the area of that piece, which is 9/4. That's the exact answer. We could always punch that into a calculator to get the approximate area. Okay, so that's what we're looking at here. And again, another way of thinking of it here is you can think of it in terms of you're doing the area of that semicircle piece, cut right there, that slice of the pie, if you will, cut to the center, and then we're taking off the area that's formed by this little sliver of this thing. Okay, and so that's how we can approach that problem. Okay, that's how we can actually approach that problem and compute the area. So a little more difficult again because we can only do integration. We can only do integration on these problems when we're dealing with, I don't know why my slider there is moving. We can only do integration again when we're actually dealing with actual areas that we're working with. So that's kind of how we do it. You could have also done it starting at pi over 4 and going to pi over 2 by looking at the blue function as the outer function, right? And then the black one as the inner one. You could have done that and computed the area of this piece, and then the area, could have taken that away from the area of that circle as well. So a couple different ways you could have started it, but this is the idea of how we want to approach